I guess more people will be joining, but in order to not to be late, I will proceed to present the structure of this webinar. So in the first place, welcome all of you, especially to our main speakers from the Recycleize Consortium and also from Dare2X, which are two related initiatives in the framework of energy storage. So today we will be discussing this and presenting these two innovative projects in the framework of energy storage, and also introducing and explaining the concept of the Power2X, which will be explained by our project coordinator, Christian. He will be giving this introduction right after me. And then Simon, also from the Recycleize Consortium, as all our speakers are coming from the Danish Technological Institute, will present the solution behind Recycleize. And last but not least, Christopher will introduce the solution behind Dare2X. The idea is to give an overview about these two projects and how are they contributing to the energy storage sector. Last but not least, since we want to have an interactive session, I will encourage you to use the Mentimeter application. I will later explain you the basic instruction so you can participate. But if during the presentation you have any kind of questions, feel free to ask us through the chat, which is activated, and you can ask all your questions there. And after the presentations, or at the end of all the presentation, I will address your question to the corresponding speakers. So just some webinar notices. The session is being recorded in case you want to access in the future. We won't share any personal information, so we will be complying with the GDPR rules. Also, make sure that your microphone is muted. I guess by default you cannot activate it, but just in case. As I said, use the chat function to enter your question anytime, and I will address later to the speaker. Last but not least, I will explain and I will share with you a link through the chat so you can participate in the Mentimeter activity, because we also want to know some feedback from you. Well, I didn't introduce myself, but I'm Pablo Morales Moya, Communications Manager at Sustainable Innovations. And my role in the Recycleize project is taking care of the communication and dissemination of the project, which involves basically this kind of sessions, as well as the social media, website, and all the activities related to disseminate the project outcomes. I think it's better if I give the floor to our speakers so they can introduce themselves, starting with Christian.
Thank you, Pablo. Yes, my name is Christian Kallesøe. I'm a director at the Danish Technological Institute, and also the coordinator of Recycleize, which Simon will present the results from later. And of course also will give the introduction to Power2X here today.
Thank you, Christian. Simon?
Hi, I'm Simon, or Simon Bitscheider. I'm a researcher here at the Danish Technological Institute, and as I said, I will, as Pablo already said, I will speak about the Recycleize project, which we have been working on for the past 3 years.
And Christopher?
Hello, I'm Christopher Vilsgaard Pedersen from the Danish Technological Institute. I'm a team manager here and also the coordinator for the Dare2X projects, which I will introduce later in this session.
Thank you. So, as I said, during the presentations, feel free to ask any kind of questions. Now I would like to give the floor to Christian. So let me stop sharing. And feel free to share your screen, Christian.
Yes, do you see it?
Yes.
Good. Okay. Thank you, Pablo. Yes, I will give a small, short introduction to energy storage and to the Power2X concept, which both of the two projects today, of course, are working with. So if we look at the current world situation, we all know how the amount of CO2 in the atmosphere is going up. It's going up a lot over the last 60 years. And we've also seen that there is a correlation between the amount of CO2 in the atmosphere and the rise in temperature. So Of course, we need to look at how to reduce our CO2 emissions. We have the Paris Agreement that have set a limit of 1.5 degrees, and we of course all hope that we can stay below that. So one of the ways to reduce the CO2 emissions is to have renewable energy, so energy from windmills, energy from solar cells, and so on. And this graph here to the left, this shows the energy, the European solar energy production in 2021, 2022, and what we can see here is that the production from the solar energy is not surprisingly fluctuating as a function of the year. So in the winter months, we don't have that much energy production from the solar cells. In the summer, we have a lot. We will not see the same trend with the wind energy, but we'll also see fluctuations over days here, depending on how much the wind is blowing. And we can imagine in the winter time, where you'll have no wind, no sun, that you will have almost no energy production. So when we talk about renewable energy, we need to have a lot, so we can actually work with depend on energy in every given instance. And even also if we just look within a day for solar energy, not surprisingly again, we have a strong production in the middle of the day and no production in night. So what can we do, for example, to store this energy? Here we have various ways of storing energy, this graph shows various energy storage methods where you have one axis is showing the capacity, how much can you actually store, and the other axis is showing for how long time it makes sense to store with the various methods. Here we see that if we want to store energy for more than a day, maybe more than a week, we need to look into storing energy in chemicals. Batteries and other flywheels and so on can maybe help with small fluctuations during the day, but if we want to store for a longer time, we need to look into converting it to energy. So how do we do this? This is actually what we call the heart of Power-to-X. So it's converting power to something, here the electricity. And for example, that could be hydrogen. This figure here, that shows the typical pathways for Power-to-X. So we start with renewable energy from, for example, wind or for solar energy. And then we use that energy to split water into hydrogen and oxygen, if using what is called electrolysis. The hydrogen is, as a graph here to the right, it still shows a very good energy carrier. It has a high energy density if you compare it to how much it weighs. You can also further synthesize it into to other e-fuels or chemicals utilizing, for example, captured CO2 or nitrogen from the atmosphere. These fuels and energy, fuels, they can then be used instead of the fuels we use today. So we can use fuels within these various fields, industry, agriculture, where you use a lot of ammonia, transportation, heating, and also electrification. For example, if we need to convert some of the fuels back to electricity again. And when we convert this hydrogen into these fuels, we can have even higher densities, energy densities, than we can with hydrogen. So what are then one of the most common fuels that we can produce, also what we call chemical intermediates, what we like a step on the way to produce the fuels. People are talking a lot about, of course, hydrogen, which we'll also look at today with Recyclyze. About e-methanol, syngas, e-methane, and e-ammonia, which Christopher will talk about with Dare2X. So by adding, for example, CO2 to hydrogen, you can produce a lot of different e-fuels that are carbon neutral but still contain carbon. So that's methane, diesel, methanol, kerosene, DME, and so on. If you add nitrogen to your hydrogen, you can produce, for example, green ammonia. And all of these fuels, they can have very high energy densities. Some of the current applications hydrogen is a very important green fuel. You can use it in fuel cells, but it also has a very low volumetric energy density, which limits its use as a fuel for a lot of applications. So, and also you have to have a lot of area to store it. So to overcome these problems, you can actually directly convert it right away. You can convert it with CO2, for example, to methanol. You can use methanol as fuel for heavy mediums or of transportation. You can actually retrofit your gasoline motors to run on methanol. And it's easier to produce methanol than, for example, diesel or aviation fuels, which is further along down the chain. Syngas you can use as a precursor to produce chemicals or heavy-duty fuels or aviation fuels. And e-methane you can also use to produce other chemicals. You can also have it as an alternative to biogas. And then ammonia, which we're also going to talk about today. Actually, the ammonia production today, approximately 1% of the world's total carbon emissions comes from the production of the ammonia that we use today. So just by replacing that with ammonia, we can reduce the CO2 emissions a lot. Ammonia is the most important fertilizer in the world, so it's used in agriculture. But it's also thought to be the green fuel of the future for big shipping, and which then will further lower the amount of carbon emissions. So we call this the big picture. What you're going to hear about today is, first of all, how we can convert renewable energy to hydrogen. This is what we are working on in the Recycler project. And then furthermore, how can you then convert hydrogen into an e-fuel like ammonia, which Christopher will talk about in Dare2X. And yes, that was the introduction from me, and I'll give the word back to you, Pablo.
Thank you so much, Christian. I think it's time to Simon to put an example about your presentation, specifically with Recycleize project. So Simon.
Thank you very much, Pablo. I hope you all can see my screen.
Yes.
So as already introduced, the first part of this webinar will be now dedicated to Recycleize. Recycleize is a project that has been running since April 2020. And it will run out now at the end of September 2023. So we're closing towards the end of the project. And the starting point of this project was, as Christian already mentioned, to make the electrolysis of water more efficient. And in particularly, we have been looking at the proton exchange membrane electrolysis. There is other technologies around, like the alkaline and the solid oxide, but we have chosen PEM because it has a series of advantages, namely that it has a very good capability of running dynamically. So it has fast dynamic response times. It can be also very efficient because it has like very low ohmic losses over the cell. Which means that it can operate at high current densities and reduce the operational costs. And also it can run in pressurized mode, which also helps when having to store the hydrogen at high pressure. The gases that come out have very high purities, and you only run deionized water in the PEM, so you don't have any corrosive electrolytes, like, for example, in the alkaline system. However, there is one big drawback with PEM electrolysis, which is the very, very high use of critical raw materials. And in particular, when we're looking at the anode electrode, we have to use iridium and ruthenium, which are elements that have an extremely low volume, which also means that they have extremely high capital costs. So the production rates are very low. Their mining is responsible for extremely high CO2 emissions. As you can see in the table below, they're orders of magnitude higher in comparison with traditional metals such as nickel, manganese, copper, and titanium. So, of course, the starting point of Recycleize was that we want to, first of all, manufacture highly active and more sustainable oxygen evolution catalysts, where we either reduce or completely eliminate the use of critical raw materials, which means reducing the CO2 emissions and reduce the cost of the electrolyzers. But at the same time, also, we wanted to establish a recycling scheme which would mean that we could close the loop and instead of disposing of the materials, get them back and be able to reproduce new electrolyzers with the materials that come from spent electrolyzers, which would of course also reduce the dependency of the European Union from import from the outside, because most of these critical raw materials are of course not mined in the European Union. Which means that the goal of Recyclyze, to put it very shortly, is to overcome the main existing barriers for the PEM electrolyzers and to penetrate the market by having a lower price, a higher accessibility, and a higher performance of these electrocatalytic materials. In terms of results, we looked into synthesizing new and stable catalyst materials with improved activity and reduced critical raw materials content, as mentioned. We also wanted to look into some manufacturing processes for the catalysts that would make them more efficient. We also want these manufacturing processes to be scalable, of course, and we also want recycling processes for these critical raw materials to be scalable. Mainly for the critical raw materials, but also for the other elements that we might add into the catalyst. We also looked into directly reactivating the membrane electrode assemblies and setting up some recycling strategies on the whole PEMEX system. So in the end, we would like to reach a circular economy using the recycled materials to prepare some fresh catalysts and or use the reactivated MEAs to produce some new electrolyzers. To show it in a graphical way, the process would start with the catalyst production, where we would look into supported catalysts to increase the activity of the catalyst materials. Then we would fabricate membrane electrode assemblies that we would be used in the stack. The stack would then be tested and its performance would be analyzed over a certain time, and also with accelerated stress tests where applicable. Then the stack would be dismantled again. And here it's the big difference. So instead of sending the materials to disposal, the materials would be sent back to be recycled and upcycled. So either by obtaining directly new precursors for the catalyst materials, or by reactivating the membrane electrode assemblies to be put back into the stack directly and making the loop even smaller. So in terms of catalyst materials, as I mentioned, we were looking both into CRM-free and low CRM materials. The first thing I will talk about is how our work has been done on CRM-free catalyst materials. And in this case, the most promising route was to actually use manganese oxides that were combined with either gold or silver nanoparticles, and also creating some composites. So the manganese oxides were either synthesized directly with the gold or the silver nanoparticles, or the silver and gold nanoparticles would be deposited onto the synthesized manganese oxides. The performance that we got with these materials is actually pretty promising, especially considering that it's materials that are absolutely not optimized and that have a lot of challenges also with the stability and with the activity, and that are completely CRM free. And especially when you look at the graph here on the right side, we realize that there were a lot of issues with creating a layer that would be actually be active and also not have transport limitations. So we think that, especially when looking at the very low current operation of these materials, that by optimizing the layer, we could reach some very good activities with these completely CRM-free materials. In terms of low CRM materials, as I mentioned before, we decided to create supported catalysts. The reason is that if we use a conductive support and only a smaller amount of catalyst nanoparticles, we can increase the surface area of the catalytic material, which is actually the most important part when you want to increase the efficiency of your electrochemical reactions, by reducing the bulk amount of catalyst material that you actually need. In these terms, we looked at we tried to obtain some support materials that would have conductivity similar to carbon, which of course cannot be used at the anode of a PEM electrolyzer because the carbon would simply be oxidized right away. And our most promising candidate, as you can see here on the right, was ATO, which stands for antimony doped tin oxide, which has a conductivity which is in the same order of magnitude, at least, of carbon supports. And also we managed to produce it with a fairly high surface area. And we also upscaled this to a much larger production. So first we tried with a flask scale, and then we moved it to a big batch reactor. And we still managed to obtain very similar conductivities, slightly lower, maybe because of the porosity of the material, with also very high surface area. After synthesizing the support, we would then deposit our catalyst nanoparticles on top of it, which we did here at DTI using hydrothermal flow synthesis, which means that we have the support and the iridium and the ruthenium precursors that are pumped through this reactor. In the hot zone, the precursor salts become unstable all of a sudden, which means that the metallic ions will precipitate on the support material and form very well distributed nanoparticles. And this process can basically run continuously, which means that it's an extremely scalable process, and you can produce anything from half a gram or even less of catalyst, and all the way up to at least tens, 20s of grams that we have used for the stack production. In principle, we could have produced also more, but it was out of the scope for the amounts that we needed for the stack. The flows are pressurized to 300 bars, and the temperature in the hot zone is usually kept between 250 and 300 bars. And then it's cooled down to room temperature right away and tapped and subsequently cleaned with centrifugation and drying. Another thing that we also did during this project was to actually boost the activity of iridium ruthenium further, because literature was suggesting that adding nickel into the catalyst material or into the synthesis would promote a formation of the Hollandite structure for iridium oxide, which is much more active for the OER reaction. And indeed, by adding some controlled amounts of nickel in the synthesis, we could reach a substantial improvement of the catalyst activity by obtaining this more amorphous structure that was a mixture of rutile and the Hollandite structure. And just to show how our catalyst compared with some more traditional catalysts, these are some RDE measurements where you can see on the complete left side how unsupported iridium oxide would perform, and how by progressively optimizing the composition of our catalyst, we managed to actually reach a significant improvement in the OER activity of the catalyst material. And this formulation was also passed on for the stack production. This brings us now to the next step, because once the catalyst material is synthesized, it also needs to be put together into electrodes and then also in the electrolyzer system. So first of all, we actually looked into how to optimize the catalyst loading of our synthesized catalysts. And we realized that in principle, it was possible to go to very low loadings while still retaining a very high activity of the single cells, which was very promising, of course, in terms of our goals for reducing the CRM amounts in our cells. However, when looking at the stability over time, we realized that very low loading means that the layers of this catalyst material are very thin, which means also that over time they degrade much faster. So this, of course, means that it doesn't mean that it cannot be done with low loading, but it means that a lot of optimization needs to be done to make the layer more robust and to avoid the degradation mechanisms that would make us lose the activity so quickly. We also looked at the difference between using platinized and non-platinized titanium felts for the current collector at the anode. And we realized that with platinized PTLs, we can actually reach maybe a little bit higher activity, but it looks like the degradation rate with or without is not really affected, at least in these 100 hours of the long-term operation for the single cells. It's also to be noted that every drop here in the graphs was a moment where the performance was actually pushed, so where the cells were stressed a little bit more. So the fact that then they recovered and that we managed to stay basically on track with the degradation was a really good sign in terms of the stack production. Then, of course, the production needed to be scaled up to the stack level. So we moved from the 2 by 2 square centimeters single cells to much larger, around 10 centimeter in diameter cells that were mounted into this short stack of 14 cells. And this stack was then tested at Heisenta in Austria. This was the first generation stack, and now we're in progress with creating the second generation optimized stack for the end of the project. In terms of stack testing, there was also a lot of work going on, which was mainly a cooperation between Heisenta and Prüfrex, where Heisenta was actually performing the tests and recording a lot of data during the test. And then the data would be used by Prüfrex to create a model of the whole plant that would then be fed back to Heisenta in terms of trying to obtain a model-based control where you would be able to reduce the amount of sensors that you have in your balance of plant, basically, which means reducing the capital expenses of creating such an electrolyzer, and also controlling your processes much more accurately. And also by using a model, you might be able to lower the stress for all the stack components. Finally, I'm going to talk a little bit about circular economy efforts in terms of materials recycling and sustainability. So once the stack reaches the end of its life, a lot of things need to happen for the materials to be recovered. First of all, the stacks need to be dismantled, and a lot of the metallic elements need to be either recycled or directly reused, especially concerning the titanium plates and the iron components. Then the MEAs, as we said, we tried in situ reactivation, but that didn't really work out. So we sent it for actually recycling of the materials, which means that the MEA needs to be pre-treated to separate the membrane from the solid residue. And then the solid residue can be used to basically leach out the precious metals, and that then will be refined and re-obtained in a precursor form afterwards. And especially here also a new distillation process for the ruthenium recovery has been found and is in the process of being patented. In terms of stack disassembly, Acurec in Germany has also created a process where after disassembling the stack, you would be able, with some machine learning and image recognition, to figure out where the MEA is located, and then the robotic arm would be able to go and pick up exactly the membrane electrode assembly and remove it from the band and put it on for further processes. So this would actually help automatizing the separation process further down the line. In terms of how the different materials were separated, this is a little bit of an overview that shows how complex this actually is, because one thing is the dismantling and the sorting, where you can easily obtain the titanium from the structural parts, for example. But then once the MEA is delaminated and the solid catalyst is obtained from it, basically for each different element, you need to use different solvents and ion exchange elements to be able to separate, for example, the ruthenium and the tin and the antimony from the support, and then the iridium and the ruthenium from the anode catalyst, and the platinum from the cathode catalyst. So this whole work has been done by the University of Freiburg in Germany, and it's been a really big part of this project. And as you can see, we managed to obtain salts of both platinum, iridium, and ruthenium that will be further tested to produce new catalysts very soon. So if I have to sum up a little bit what the progress of Recyclyze has been over these last 3 years, we saw that the non-CRM catalysts is a challenge, but it has potential to be used. I haven't mentioned it before. This was a big part of the work that was performed by the University of Bern. Using the support that in this case was produced by the Fraunhofer ICT in Germany has shown a great potential for reducing the amount of CRM in the catalysts. Using non-CRMs with iridium ruthenium could also be a way forward to create more active and more sustainable catalysts. Now the second generation stack is being assembled here by Blue World Technologies in Denmark for the system implementation and the demonstration now during the summer. The recycling scheme has been established for all the critical raw materials, and soon we will get the recycled materials back, and we will try to create some new catalyst materials with these recycled materials. And with this, I would say thank you very much, and I hope it was a presentation that gave you a little bit of insight into how PEM electrolysis can be made more sustainable.
Thank you so much, Simon, for this inspiring presentation. I just want to remember that if you have any kind of questions, you can drop us in the chat box or directly to the speakers. So I think it's time to move with the Christopher presentation.
Thank you, Pablo. Yes, yeah. So I'm introducing the Data2X project. So the Data2X project has only been running for little more than half a year. So we don't have that many results yet. So I will more introduce the concepts in the project and the reasons why we are working on this. So ammonia is today mainly used for agriculture. It's an important part of making fertilizers, and without it, it would be difficult to feed the whole population of the earth. The problem with the way ammonia is made today is that it is a CO2 emitting process. You are basically using natural gas to get the hydrogen, and then hydrogen is reacted with nitrogen in this Haber-Bosch process to produce ammonia, and then the ammonia is transported to where it's needed. So it's produced on very large scale in some centralized plants where you have access to natural gas. And yeah, this process alone causes the 1% of the global CO2 emissions. And let's continue. Yeah, I also just wanted to introduce like the different types of ammonia, and is similar for hydrogen right now, that there's different colors of hydrogen and there is different colors of ammonia, and that's basically how it was made. So the traditional method with natural gas that is steam reformed into hydrogen, and then gas is driven Haber-Bosch reaction, that's called gray ammonia. If you capture all the CO2 for that process, then suddenly it's called blue ammonia. But if you want like a green process, so green ammonia, then you cannot have any CO2 emissions. So basically you will use renewable energy to make hydrogen from electrolysis, and then have an electrical Haber-Bosch process to produce green ammonia. Just to introduce a bit how the process works today. So this is like a process diagram. On the left is what we have today, and on the right is how an electrical system will work. And like most of this diagram is just how you convert natural gas into hydrogen, which releases a lot of CO2. And then you have a high pressure process to making ammonia. And after you produce the ammonia, then you have a condensation step to separate the gases. And then you have to compress the gases again, heat them up to run the reaction. So this requires a lot of energy. And the reason this is so complex is that they've tried to optimize it over the years to have it in the most energy efficient process with a lot of heat exchangers and such. The electrical system on the right side is much more simple. Basically have an electrolyzer to make hydrogen, pressure swing adsorbent to get nitrogen from the air, and then you can have like a similar process with the high pressure, high temperature ammonia synthesis, and then a condensation step to separate it. It's not the most energy efficient way. So before we started the project, we looked at some techno-economical analysis of sort of if you want to go green, what kind of options do you have? And one challenge of the high temperature, high pressure process is that it's not very dynamic. You can't really turn it on and shut it off because it takes time to heat up the system. So what people have looked into is if you can make more dynamic systems by lowering the pressure and different options. So basically there's like 3 different types. So the one called A is basically what you have today. So a high temperature, high pressure reactor, and then a condensation step to separate out the ammonia. Option B is that you again have this high temperature, high pressure step, and then use adsorbing materials. So it's basically materials that can adsorb ammonia, and then you switch between having one reactor that adsorbs and one that desorbs. And the option C is basically where you integrate this adsorbing materials with the reactor, and in that way you simplify the process. On the right side, this is like a bit complicated graph, but basically the red bars are energy efficiency and the blue bars are like capital cost of building the plant. And the first columns are the current methane process. The next columns is what happens if you go down in pressure. And basically you lose all of your energy efficiency and it becomes extremely expensive to run the process, mainly because of the condensation step. If you convert to an electrical process with adsorption, it becomes cheaper as long as you are at a certain pressure. So the only way to make like a low pressure, low temperature process is if you have this combined reactor with adsorbing material. So you are synthesizing and separating the ammonia at the same time. And that should, in theory, be able to produce the ammonia with the same energy efficiency and lower capital costs. But these different technologies have different technological readiness level. So if you just wanted to do an electrical Haber-Bosch with an alkaline electrolysis, that's 8 or 9 TRL level, means that that's something you can buy off-the-shelf component. And then depending on what type of electrolyzer system, then maybe it goes a bit lower. The most interesting options, so like electrochemical, very low TRL, but have been demonstrated. This low pressure process is also in the research phase. Non-thermal plasma, which I will go more into, is also very low TRL. So there is alternatives to this classical process, but many of them are still in the research phase. So this brings me to the Dare2X concept. And so what we wanted to achieve in the Dare2X concept was a process that is dynamic. So it fits with renewable energy, both solar and wind. and we want it like completely electrical, so there's no CO2 emissions, and then we want it decentralized. So you just produce it where it's needed, so you don't need to transport it. And this also makes it easier to utilize like local solar plants, local wind farms. And then it can be used, for instance, for like a collective of farms to produce their own fertilizers, or potentially for shipping in the future, especially like long distance shipping. There, the maritime sector are looking more as ammonia as the long-term solution. It's difficult to find other fuels you would be able to produce as cheaply. So the DAR2X reactor is a plasma reactor and a non-thermal. So that means it doesn't need to heat up. The plasma is what activates the reaction. And then we have a mixture of catalyst optimized for the plasma reaction and sorption materials that can absorb the ammonia. So you have this synthesis and separation process step in one. That's the overall idea. And so why plasma? So what happens when you have plasma is that you activate the nitrogen bond, and basically breaking this triple bond that nitrogen gas have is the biggest challenge, and why the Haber-Bosch process normally works at high temperature, 400 to 500 degrees. But with the plasma discharges, you can actually destabilize that bond, and that makes it easier to separate. And actually, the plasma alone can produce ammonia. The disadvantage is that the plasma can also run the reverse reaction, where you crack the ammonia into nitrogen. So the way we want to solve that, and that's another reason for using this sorption materials, is that if you store the produced ammonia in pores, then the plasma can't access these pores, and in that way you avoid the reverse reaction. The disadvantage of the plasma is that currently it's has a lower efficiency, and that's basically things that is wasted, like heat or competing reactions that we don't want. Another interesting thing about plasma from the catalyst point of view is that because it sort of destabilized the nitrogen bond, it changes like the optimum for which catalyst. The orange curve is like the classical catalytic volcano for ammonia synthesis, and there you can see that ruthenium is the best catalyst. Iron is the one that is most widely used, but that has more to do with how cheap iron is compared with the ruthenium. But if we have in a plasma process, then you shift the volcano, so suddenly it's different materials that is on the top. So theoretically, it's expected that cobalt or nickel should be the best, and overall should produce a higher, better kinetics than the current ruthenium does. So looking this, then it's like copper and nickel. Just coming back to the efficiency of the process. So this efficiency axis here is for the ammonia synthesis alone, ignoring the energy used to produce the hydrogen. And you can see the current plasma technology is about an order of magnitude worse than the classical Haber-Bosch process, and this is what we want to address in the DAR2X process project, with new catalyst, new sorption materials, new reactor design. So we hope to come closer to Haber-Bosch or the energy efficiency levels of the Haber-Bosch process, and longer term be able to compete with it. So theoretically, the plasma process should be able to be more energy efficient. And yeah, the figure on the right is again just to show this concept of producing ammonia and then storing it in adsorbing material. Another problem, I think also Recyclyze touch upon this critical raw materials. So the EU Commission have identified materials that are like critical, so materials we import and use in large amount. So this is also something you have to think about when developing a technology, that we want to avoid the use of these materials, and this also helps then that nickel is one of the materials on top. But we want to look into making different alloys, so we get similar performance, but without having the CRMs, and also using promoters. The main idea, which I've said a few times, is that you have this synthesis materials. So C is for catalyst, A is for adsorbing material. Have that together, and then you have separation in one step. But we will also explore the possibility, like you can say, an backup plan is to design a adsorber unit to this that will be able to do the separation if the synthesis separation it doesn't work. And then just the main path of the project is that so designing catalyst materials that works in a plasma reactor, and there we have like an experimental pathway, and we have a theoretical pathway using DFT modeling. Then we are looking at adsorption materials, so finding the right ammonia adsorbing materials. So materials that are efficient at absorbing ammonia, and also where we don't have to heat them up too high to release the ammonia, because of course you will also lose energy efficiency in that process. And then finally optimizing this plasma process to achieve the higher energy efficiencies. And this we hope to combine these three pathways into a new lab prototype that can demonstrate the better energy efficiency. I think already talked a bit about it, but we also want to integrate the catalyst into the sorption materials. So you have the catalyst on the pores of the sorption material. And here is a picture of a simple lab reactor. So it's quite simple. So it's low pressure, at normally just atmospheric pressure, room temperature. It heats up a bit if you don't cool it. So between room temperature and 100 degrees. And this is very low cost materials. It's basically glass and metal electrodes, and then a bit of catalyst. So you can get this to work. Then it's fairly cheap reactors you can build. And to sum it up, so then Dare2X is one of the pathways to decarbonizing ammonia production in the EU. And then we want to replace the centralized process to have more decentralized production of ammonia where it is needed, and also enable the possibility of using ammonia as a green fuel or for energy storage in general, and it has to be green for that to use it as that. Otherwise, it doesn't make any sense. And then our strategy in the project is combining the metal catalysts, sorption materials, and these plasma reactors. And our main focus is increasing the energy efficiency of the plasma catalytic process, so we can compete with the more centralized Haber-Bosch process. And I will just shortly introduce the consortium. So we here at the Danish Technological Institute is working on producing catalyst. University of Liverpool is designing the plasma reactors. Hulteberg Chemistry and Engineering are looking at different absorption materials for the process, and also a bit on how you can design a plasma reactor with all the downstream processes. And then we have National Institute of Chemistry from Slovenia that are doing this theoretical screening of catalyst materials. ENSO, Environmental Solutions from Spain, are looking at life cycle analysis and life cycle costing. So basically, when we develop this new sustainable technology, we want to make sure that we are following sustainable path. So that is important also to look at the environmental impact and the economic impact of the choices we take with regards to materials and processes. And then finally, Lomatov is also looking into these techno-economic and social accessibility studies, as well as the dissemination of the project. And with that, I will like to thank you for your attention and give the word back to Pablo.
Thank you so much, Christopher, also for your inspiring presentation. Since we still have a few more minutes, let me share I will share with you through the chat a link to participate in the Mentimeter activity. And let me copy also, in case you use your phone, you can also enter this code. And now let me share again the screen. Okay, so I see that many people is used to use Mentimeter, but in case you never use it, here you can find some basic instructions. So basically, you can grab your phone, type 33.menti.com, and then enter the code that I just passed through the chat, or just directly click in this hyperlink that I already sent into the chat. And now you can participate in the activity. So my first question, since we want to know a little bit more about the audience that is attending to this webinar, is what country are you from? And we see that there is people from Spain, Denmark, and Germany mostly, as well as Portugal, UK, Norway. So it's good to see that there is so many countries from Europe. Our next question we want to know from you is, what industry do you work for? So again, you can type your answers. And we see some answers. The first one is research, academia, catalysis, innovation consulting, research organization. Okay, which is quite similar to academia and research, energy, consulting and testing. Okay, so most of the audience, it seems that is coming from research, but also we have some other sectors such as energy, consulting, innovation. Great. So another feedback or another thing we want to know from you is, which technology do you work with? Non-thermal plasma, proton exchange membrane, alkaline electrolysis. We also have ammonia, surface catalysis, hydrogen production, fuel cells. Okay, it seems that many people is working in ammonia mostly. And we have a lot of answers, different technologies. Good to see. Photocatalysis, water electrolysis, surface catalysis. So very, very nice. And another thing we want to know is how useful did you find the content and the talks ideas, since this help us to evaluate the quality of the content that we have presented to you, and it helps us to improve if we organize upcoming webinars or informative sessions. It seems that most of you found the content very useful, so we are very glad. So it's around 9 point something. It's moving a bit. So thank you so much to evaluate. And another important information is, or question that we want to ask you is, are you likely to use this information in your future work or studies? And it seems everybody's answering yes. We also have a no, which is actually very useful. It's if you want to let us know in our emails, or even if you want to ask in the chat if you miss any kind of information, feel free also to let us know. And I'm sure our speakers will be more than happy to answer or to provide you more information in case you couldn't find it in this webinar. Okay, and the last question is, would you be interested to know or collaborate more about the Recycleize and Dare2X project? Both, not for the moment, no more, both. Okay, good to see. Good to see these nice results. And just, I would like to inform you that as Simon explained, we are in the end of the project, and we are actually starting to organize our final conference. And so we invite you to follow our social media channels in order to share with you the registration link. And I think, yes, that was all the the questions. So thank you so much. And I basically don't have, I would like to check the chat. Let me put the presentation again, because I think we still have time for one question at least. Okay. So I received some questions during the presentation. For example, if we are going to share the PowerPoint presentations, since I see the most of you have the interest of having this presentation, we invite you to follow Recycleize and Dare2X social media channels, so we will compile all the presentation and we will share it in PDF. And if you need any specific presentation, you can just mail us. Here you have the main channels. And I have a question for Christopher. Are there any safety issues with using this reactor with plasmas for splitting N2 with H2?
Yes, good question. So there's no, you can say there's some general safety concerns with ammonia, but using the plasma reactor, there's no additional safety concerns. So ammonia is toxic, so you have to take that into account when you design the reactor, especially also when you design the systems around it. So like safety systems are quite important. I think there was also someone commenting the use for ammonia as a fuel earlier, and of course that is also a concern for the for the maritime sector, and also something that is looked at separately.
Thank you, Christopher. It seems there is no more questions, but again, if you want to ask something later, feel free to email us and I will address your question to the corresponding speaker. No more from my side. I just want to thank you all the attendees and also to the speakers for such as amazing presentations. It's been a pleasure. We invite you to follow both projects because for sure we will organize our final event in Recycleize, which will be online in September. So hope to see you all there. We will share with you new information. And again, thank you so much for attending this webinar, and thank you so much also to the speakers of today.